So I've mentioned that neural networks are really a cutting edge of machine learning, and they have been for some time, and I expect they will continue to be for some time in the future. And unfortunately, when like we're doing a kind of intro course, you can only do so much. You can't actually do a lot of the cutting edge stuff. We just don't have the tools for it. But that doesn't mean we can't play around with some stuff, which is pretty cool. So I wanted to show you at least three things where you can get an idea of what these networks can do, how powerful they are, and in particular, kind of get a better idea just playing around with things, kind of how they operate. So I'll post all these links so you can play around yourself, but just kind of like see what these things can do. I'll just kind of walk you through them, but please explore at your leisure. There's just so much cool stuff. So the first one is TensorFlow Playground. So both Google and Facebook have their own deep learning neural network toolkits that they're pushing kind of in competition with one another. Google's is called TensorFlow, and has packages that kind of wrap TensorFlow, things like Keras, and Facebook has one called PyTorch. And so they do similar things. They're different platforms. You probably know one better than the other. If you're in the field, but you probably have to know a little bit of both just to kind of get through. I have used Keras quite a bit, but I've never really used PyTorch. It was gaining in popularity as I was kind of transitioning out of this work to do some other stuff. So here is a playground run by TensorFlow. So here's the idea, and it's basically exactly what we did, right? So here's the idea. We have some data. It's over here. We have two classes, orange and blue. These are our targets, and two predictors, vertical axis and horizontal axis. We can use just these two features, x1 and x2, or we can add some other features like x1 squared, x2 squared, x1 times x2, sine of x1, sine of x2, so on and so on. These get fed into a hidden layer. Those hidden layers get fed into an output layer. And so we can actually run this thing, which is really, really, oh, I'm sorry, let's just start here with one hidden layer. This is exactly what we did in R. So this is a naive network, meaning it's just these weights are randomly initialized to small numbers, and we're going to run this thing forward. So notice what happened. It's actually so fast, it's kind of hard to even see. But the network is undergoing backpropagation. So records are getting fed in, the weights are being tuned, and this is happening over and over. This is the epoch up here, how many times this thing has happened. We're using an activation of hyperbolic tangent. Regularization isn't important well, it's a little too much for us, but the idea is that it is a way to penalize you to having very strong weights, having very strong opinions. It keeps you humble in a way. And this learning rate is how quickly we're trying to move down the gradient. We can talk about why certain, in fact, let's turn the learning rate down a little bit so it takes a little bit longer to get there. So notice that we are, and then here's actually our curve of loss. So loss is the same thing as cost. And so notice that we're over, as we increase the number of epochs here, we are getting better and better and better at predicting both training and test. Both of these numbers are still going down. At some point, with real data sets, it's possible for this thing to become overfit, just like any other model. In fact, neural networks are, because they have so many different weights, are very, 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 very prone to overfitting. And there's a lot of research about how to get around this. Things like dropout, for instance, where you selectively, in each epoch, just kill some of the connections, which is kind of an interesting idea. We can talk more about that if you're interested. But we're doing great. This is good. So basically, at some point, we've basically just converged. These numbers aren't changing anymore. But what about a more complicated data set? So let's do like this one. So this is a little bit more complicated. And notice that these connections are changing as we go forward. Some of these are strengthening, some of them are weakening. And we're doing pretty good here. But notice like we're not, like it's found an interesting structure. It's saying, oh, look, it's not seeing that it's quadrants, right? It's just seeing that there's, I put a big orange thing down the middle. I'm doing pretty good, and it is. It's like only misclassifying these points right here, and maybe this one here, and these here. But it is to say that it might find a solution that works pretty well, but is different than our intuition. So what about something even more complicated? Let's crank the learning rate so it doesn't take quite so long. This is my favorite. This is a really hard one. So like, let's watch this thing try to figure this out, and fail pretty much. See it? See it overfitting? This number is increasing. Yep, we're in trouble. Oh, this stuff is so cool. So what do you do if you're in trouble like this? How do you fix this? Well, one thing we can do is add some more features. Let's see if that does it. What this allows us to do is have a richer input space, which allows us to have richer connections here. And one thing I didn't like, it's still, oof, it's trying so hard. Come on, buddy. Nope. Oh, poor guy or girl. I'm not sure whether neural networks are masculine or feminine. So let's crank this up. So again, this is the play part of this. Look, I'm going to crank the number of hidden layers. I'm going to crank the number of things in the hidden layer, and I'm going to hope for the best. One thing I haven't talked about is notice here that these intermediate features, this is the type of, so over here I have x1, and it goes from one value, like orange on the left to blue on the right. x2 is the vertical one, so it's blue on the top, orange on the blue on the top, orange on the bottom. These are the intermediate things. So this particular node is detecting this part in here. This part node here is, and it's like I can't point because it just doesn't work. But each one of these nodes is creating a more and more complicated pattern. And notice that this is pretty good. It's not super stable right now. And neural networks do jump around a lot when they get more complicated like this. The gradient descent is not always smooth, but it's doing a much better job. But anyway, like, there's a lot you can do here. Like, so I encourage you to play around. We only touch the surface here. You can increase the noise, which makes this blurrier. You can increase and decrease the batch size, which is interesting. You can try different activation functions, including the ones that we talked about. Sigmoid is the same thing in principle as a logistic. Linear is linear, and so on and so on. But anyway, there's a bunch there. One other thing I want to talk about is this. So this is actually becoming old news at this point, which is so remarkable. But this is a style mimicker. And so here's the idea. We feed in a bunch of different, we feed in an example of a artist. So in this case is Van Gogh. We feed in examples of Van Gogh's art, and then we feed in a picture. And the neural network has learned what Van Gogh's style is. Like, it's learned his style, which is an abstract idea, but is represented quantitatively in the neural network itself, in the hidden layer. And this is getting a little bit beyond what we can talk about, but the hidden layer is actually encoding at some point his style, and then we can apply that style to any picture we want. So here we've taken this picture, we've applied the style from Starry Night, and here we are. We have this this particular instantiation, and there are many, 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 many others. And this is to the point where, like, you can implement this yourself. It's just really, really remarkable. Are they going to try to? Oh, interesting. Oh, neat. This is new since the last time I've seen it. Yeah, this is all new since the last time I've seen it. Really, really remarkable. Anyway, play around. Take a look. This is another one that I like, and this is where neural networks are getting increasingly scary. This person's not real. So this person does not exist.com, and in fact, this person does not exist. Which is just remarkable. Each time you refresh the page, the neural network generates a new fake person. So the training data set here is images of real people, and the output of the network is a fake person. So here's how this works. It's called the generative adversarial network, and it's essentially two neural networks together. One of them is trained to generate fake images. It's fed in a training data set of real images, and its job is to generate fake images. And we have another neural network whose job is to detect fake images. So we feed it in, we show it either a real image or a fake image, and it has to guess whether it's a real or a fake. So here's how this works. The generator network generates an image. The detector network tries to guess whether it's fake or not. If the generator can fake out the detector and like fool it into thinking that a fake image is real, the generator network gets rewarded. If it fails to fool the detector network, it gets penalized. And back and forth. And the generator, obviously, the detector, if the detector doesn't detect a fake image, it gets penalized. If it does detect a fake image, it gets rewarded. And so these two networks are going back and forth. They're evolving together. The generator is getting better and better and better at fooling the detector, and the detector is getting better and better and better at recognizing fakes. And if you do this for a long time, you get to this, which is images that the generator can generate and the detector can't detect. which is just amazing. So every one of these things is fake. Every single one of these people is fake. And sometimes, okay, so it's interestingly enough, the way you can often tell if you're looking at these things is the background. Do you see this? Because the thing is trained to recognize, to generate faces. But oftentimes it screws up the background. Like the background doesn't look quite right. The other thing that I've noticed is that, see this background, it just doesn't look real. I mean, it looks kind of real, but it doesn't look real. Oftentimes, and I think they generate them on purpose, it mismatches women's earrings because the algorithm knows that women should wear, that women often wear earrings in these pictures. And again, by often do I mean in the training data set, the lots of women in the training data set are wearing earrings. Here's a good example. But these earrings don't match. These earrings don't match. But what's so interesting is that the algorithm has learned that eyes should match in color. Like you very rarely see heterochromia where the people have different eye colors, but you do see things where earrings don't match for whatever reason, which is just so remarkable. But like, I can't tell. Like this one, this is a real person. I can't tell that this is not a real person. Like, there's a perfect example. Earring, no earring, right? So the algorithm has learned, and I'm not sure what's going on up here. I'm not sure what kind of hat this is, but the algorithm has learned that eye color should match, that faces should be roughly symmetric. It just blows my mind. It really, even as someone who works in this space, it's just like, I could just stare at these things forever. It's really, really remarkable. The other one I wanted to show you was Deep Dream. I forgot to do this one earlier. So Deep Dream is much the same. It is applying, it's kind of hard to describe, but it is applying both. You can do the same style thing that we did earlier and apply a style to a particular picture. So here, this is actually a great example. They're doing the actual picture on the left and the style applied picture on the right. But then we can also do in this iterative process where you're feeding the thing back into itself, and they call this Deep Dream. And it's really, really, really remarkable. Like if you watch some of these videos, and I don't want to right now because you should just sit there and watch them forever. But they are they're incredible. They really are. It's pretty remarkable what these things can do. And they just keep, like every time I come back, there's something new that you can do with these things. But these are not to be the end of the story. It's basically to give you a place to start exploring with these things. And I love talking about this kind of stuff. So if you're interested in learning more about neural networks or applying these in a particular situation, just let me know.